Hello, everybody, and welcome to the first lesson of the hands-on optimization masterclass, where we are focusing on supply chain problems. We are going to build from scratch supply chain solvers, production planning solvers, network optimization solvers. We are going to talk about lot sizing, campaign planning, shelf life, and a lot of other concepts that appear in the supply chain. So we are going to learn the modeling techniques. So how do we look at the supply chain problem and how do we model it? What techniques do we need to use? And we have Felipe here from AMPL who built a custom-made app, which we will be using to practice. And we are going to present it a little bit in this session. And then in every session, you will use it more and more. The first class will focus on the introduction of the supply chain solvers, and in particular the core equation there, because all the solvers in supply chain have an equation which is central and determines the way the solvers work. We're going to talk about the supply chain problem, what's particular about it, and how do we look at it, because this course is aimed to teach you how to think about supply chain problems, and then how to translate that into mathematical concepts and further into solvers. The two main types of supply chain problems I already mentioned, the production optimization and network optimization. And Felipe is going to tell you a little bit about AMPL and show you the app. I want to take a minute to say why do I think AMPL is a good tool for optimization. It's designed for optimization, so it has a lot of very strong features which help us, especially with a super complex problem. Because when we talk about Python, which is very popular and very good, but when problems have a certain complexity, they in Python is a little bit hard to express those expressions. Also, as we will learn in the next session, when you build a solver, you have the first phase, which is the phase of building the model. And that in Python, when the models get very large, becomes very, very slow. Whereas AMPL also has optimized this part, that you can build very large models in a very small amount of time. And lastly, it's very easy to use, so you don't need to be an expert programmer. You just need to learn a little bit the syntax, but more you need to understand the mathematics of the equations, and you should be able to read code, change code. But the purpose of using a tool like AMPL is that, for example, when there is an issue, it's like you don't spend too much time debugging the programming language, but the optimization model. And a quick introduction about myself. So I'm a mathematician and I work in supply chain for 11 years. My specialty is production planning, so I know a lot about operational, tactical, and strategical business contexts. I also have done a lot of projects of campaign optimization, network optimization, and some particular cases of optimization like blending or packing optimization. I'm also a planning system architect. And now I will let Felipe introduce himself.
Hello, I am Philip from AMPL. I've been working with optimization since 2008. I've worked with many different problem types and also different solution methods, essentially seeing what type of solution methods work best with each different problem type. Mathematical optimization was often my go-to tool, especially as like initial approach, because in most cases is the initial and also final, essentially very hard to beat with anything else, and quicker because you just write the model and it's done. During that time, one of the main models that I developed was a state-of-the-art model for cutting and packing that has been used for several years all over the world to fully operate factories and saving a lot in terms of waste materials. Before they were using an heuristic method that was very suboptimal, and now the waste was reduced to almost zero, resulting in massive savings. In 2016, I joined AMPL even before finishing my PhD, because I was really interested in going to the industry to really see these problems being used in practice. I was not so much interested in theoretical stuff. I became head of development, and at AMPL I work mostly in the integration with Python and cloud deployment.
Okay, thanks, Felipe. That was a great introduction. So let's start with the supply chain problem. So what is the supply chain problem? As we know, in supply chain, we have, let's say, three types of concepts in the sense that we have production facilities, factories, here shown as bakeries. We have distribution centers where we keep stock, and then we need to see how it's best to distribute the stock to the customers. So you can meet the demand of the customers via a distribution center or with shipments from the directly from the production facilities. So the supply chain problem is we need to see how can we optimize where and how much to produce to meet demand such that we respect the capacity constraints of the factory, like resources, labor, and so on. We want to keep the ending inventory minimal and the costs optimal. Here I mentioned the transportation costs, but you also have production costs. And of course, if the ending inventory is minimal, you have also optimized your holding costs. So we mainly have two types of decisions: where to produce and from where to deliver to meet the customer demand. And this is what we are going to talk in this course about this production optimization, network optimization, and how the solver takes those decisions. So what's particular about supply chain planning? What differentiates this from, let's say, energy optimization or, I don't know, vehicle routing problems or other type of problems, is that you have buckets. So the planning is done in daily buckets, weekly buckets, monthly buckets, and so on. And what's important about the buckets is that you carry over inventory between one bucket to the next. And this means that when there is a problem in one bucket, it carries over in the next bucket. And this, I took here an example. This is basically a planning view, a simplified planning view. This is what the planners look at when they start their system. They say, well, what are we going to check today? Let's check our ending inventory because this is very important. And let's assume here we don't have targets. So the ideal is that our ending inventory is 0. If it's 0, fine. I don't need to check anything. But how do all those planning view work? So what you do is like you look at the starting inventory. You subtract the demand. So this is the customer demand. You add the production. So what is the how much you can produce that bucket, and then by doing a little bit of maths, you get the ending inventory. And here in the next bucket, we see that the ending inventory has been carried over. Now I have again a bit demand, and the production is even lower than in the previous bucket. Maybe a machine broke or something else happened. So our ending inventory, it's already problematic. So now the planner says, well, I need to check what's happening here. How can I remedy this? So this ending inventory carries over to the next bucket. I have again quite a lot of demand. I try to catch up with the production, but it's still not enough. And then I end up in the next bucket with a very big ending inventory. So somehow here I need to take a big decision already from here. But let's say sometimes you have a frozen period, you cannot change. So you are going to have some disappointed customer, but you can catch up in this bucket. You can produce, let's say 50, because it seems like this is your more or less capacity. Here you manage to catch up, but it's not possible always. So maybe you need to purchase something, right? So you cover the minus inventory, the negative inventory, 50 production and 100 purchasing. So what we see here is that the demand is the input, is the driver. It's where the pressure comes on in the supply chain, right? And the supply is the decision. That's very important to understand that in the solver, the demand is the driver. The demand is what you start from. The demand is the first thing you check when there is a problem. And then the production, the supply is the decision. And here is a little bit more advanced planning view, where I also added the purchases, as I said. Also, of course, between facilities, you have transfers in, transfers out. And this, let's say, complicates a little bit the situation. But this is essentially all the concepts you need to understand how supply chain works. And we see here this equation, and this is the equation which I said is the core of every supply chain solver. And what is the logic of this equation is it's about the ending inventory. In each bucket, what is my ending inventory? And it's calculated by starting inventory. You subtract the demand, you add the production, you add the purchases, you add the transfers in, then what goes out? This gives you the ending inventory. This is in a production planning solver, actually. In the network optimization solver, we have also the shipments to the customers, but we are going to talk about that another time. So you see this equation is what drives the solver. And this equation is linear. And we see that this is the reason why linear programming is so powerful and suitable for supply chain, because the core of the supply chain, it's actually a linear equation. And the other particularity of supply chain is nodes, right? So on one hand, we have buckets. On the other hand, we have nodes. And nodes are typically a product location combination, right? And then it's important the material flow, what goes in and what goes out. And typically what goes in are, let's say, production, purchases, transfers in. And what goes out is the demand, right? And the transfers. The transfers you do between internal facilities. And here I have again the equation, what I just explained on the other side, on the other slide. And if we look at it and we arrange a bit the terms, we see that we can put on one side the demand part and on the other side the supply part, right? And we realize that this is actually the equation, or this is what happens in a supply chain, because what is a supply chain? Is a structure in which we try to balance demand and supply. This is a linear equation, and as I said, this is the reason why linear programming is so powerful and best suited for supply chain problem. And now let's talk about the two types of optimization we have in supply chain. So as I mentioned, we can have this production planning, production optimization, and we have the production facilities. So this is where we produce. We have the distribution centers, and the distribution centers in this problem, we know which the customer it serves, right? So this is an input. We know that customer 1 and customer 2 are served by this location, and customer 3 is served by this location. So then this is an input. This is what we know. So what is the problem? The problem is we need to take the decisions about where to produce and how to allocate that production to the distribution centers such that we satisfy the demand coming from the customer. So the demand is here, we see it, right? Here it's 500, 200, 700. So we know this distribution center needs 700 demand. The other distribution center needs 300 of demand. So how do I produce on this part of the supply chain? Where do I produce? How much do I produce? And how do I organize the movements, the stock movements in the network such that the demand is satisfied? And now we go to the other part, the other type of problem, which is network optimization. So here we look at the full network in the sense that on this side of the customers, we don't know which customer is served from which distribution center. This is optimized. So we let the solver decide which distribution center is the best to meet the demand. So in this case, we have, let's say, decisions on the both sides of the supply chain. First, how much we need to produce and where. How do we distribute it to the DCs? And then how do we optimize this part of the flow? So it becomes a bigger problem. It's a much more complex problem, but it's also more optimized, or let's say more optimal than the previous one. In the previous one, we knew those were fixed, were an input. So they were a given, and then we could only optimize this side. Whereas now we optimize everything in one go. And this is why optimization is so powerful and gives such good results. And now I will ask Felipe to share the screen, and then he can give you an introduction about AMPL.
So just a very brief introduction to AMPL. So AMPL is a modeling language that allows you to just express your problem. You write your equations, and then you can use any solver you want with it. You don't need to adjust your model to the different solvers. We do that automatically for you. And not just in terms of what the solvers natively support, you can also express things that are not necessarily supported by the solvers natively. But if it is possible to reformulate them in a way that solvers are going to support, we do that automatically for you. We are going to also show you during these sessions some modeling tricks that you can use, things that you can just express and that will work no matter what the solver is capable of. So you have your model, you can use any solver, and then you can integrate it with any kind of application or work standalone, for instance, directly with Excel. You may have your data there and solve your problems, or as done most commonly these days is to integrate with Python, where you have your data in Python, you have your model in AMPL, load the model, load the data, solve with one of these solvers, and then you retrieve the solution back into Python so that you can visualize the solution, analyze the results, and so on. Here is a table with the main solvers that apply to these sessions. These are the linear and quadratic solvers that we support. We support several more solvers, but for supply chain, these are the main ones that you need to pay attention to. The problems that we'll be looking at are mostly linear or mixed integer linear. So these two columns, so any of these solvers applies. And also all these solvers, they have an MP interface, which is the reformulation interface. So the modeling tricks with functionalities that go beyond what the solvers are capable of is available in every single solver from this table.
And here, let's say that some of them are open source solvers. Some of them are commercial.
Yes. So some of these solvers, they are open source. Some are commercial. They also have, even between the commercial solvers, there are different costs. So some more expensive, some cheaper, also different capabilities. If you need to solve a bigger problem fast, you might need a more powerful and expensive solver. If you have something smaller, you might get away with an open source solver for free. So you have all these possibilities and your model stays always the same. You don't need to worry about that. Here is a small example of an end-to-end application. Here we have a very simple model. We have sets and parameters which hold the data, then variables, an objective, a constraint, and another constraint. And you need to get the data from somewhere. For instance, using Python, you load the data from lists, dictionaries, pandas, data frames, and so on. Then you pick a solver, you solve your problem, and after that, you retrieve your solution. And in this case, we are just displaying the solution as text. But you can also do fancier stuff like having an interactive application. In this case, we have a model for production optimization, the model that is going to be used on the first few sessions. And we have the sets, the parameters, variables. And then here are some exercises that you will see how to solve. let me just show how it works here in the app. So here we have the constraint declaration, and you will just have to pick the different components and put them in the right places. And you are essentially writing the equations. Once you write your equations, you are able to, you have your model complete at that point. You are able to then load the data. And in this app, you can also change these values and see the impact they have on the solution. And once you have model and data, you are ready to pick a solver. Here we have the solvers from that list. In this case, here we are using Groby. The solver is used to solve the problem. And once that is done, we can retrieve the results and then show some visualization. In this case, we are really using some charts for a demand report and for a material balance report, where you can see the evolution of the various values over the different time periods. Going back here. So these sessions are going to be about supply chain, but just some mentions about where AMPL is used. So AMPL is used across many different industries: energy, airlines, finance, mining, all kinds of industries, especially when models get very big and complex, which also happens with supply chain.
Can you tell us what's big? Like, give us what is the biggest model you have?
So the biggest model was in fact a supply chain, and it was big, like recently, it was 500 billion variables. So wow. The supply chain models, they can grow, they can become quite massive. It is possible to still solve them. It was necessary to use a machine with 1 terabyte of RAM. So that is how big they can be.
Yeah, sounds good. Okay, and this is the last slide of this session. A little bit of introduction about the next lesson. We are going to talk about linear programming, mixed integer programming, what is the difference between them, introduce constraints programming, and what is the connection with AI ML. Then we are going to see heuristics versus mathematical optimizations, because sometimes it's good to have a heuristic, sometimes mathematical optimization is better, sometimes it's good to have them together. So for this, it's better to understand what are the strengths and weaknesses of each of them. And we are going to go a little bit technical and show you exactly the structure of the solver. So you start with the equation editor, you also have loading the data, and then this part of building the model, as we said, where AMPL is very good. It is able to build very big models in a short amount of times. Then you call the solver like Gurobi, Higgs, and so on. So I'm going to explain a little bit about this and also demo it. So Felipe is going to show it on a small model, all those phases, how do you trigger them, how do they interact, and so on. So you have a better representation about what is actually a solver or a model, because solver can mean different things. So yeah, let's say we are going to define the terminology. This is it for today. Thanks, Felipe. Thank you for watching, and we'll see you the next time.